Hello folks, this is Jennifer. Today we will talk about LeetCode 207 course scheduler. So the question is, there are n courses given a prerequisite rule and a list of courses determine if all courses can be completed. Let's think about a scenario. As a fresh-faced college newbie, I'm faced with a list of courses and their prerequisites like this. I cannot immediately enroll in C5 operation system, because it requires completing C3 data structure and C4 principles of computer organizations first. How should I plan my course selection? I can draw a diagram. I realize that C0, C1, and C2 do not need any prerequisite courses, so I will draw them out first. After I have taken C1 and C2, I can take C3. After I have taken C0 and C1, I can take C4. After I have taken C3 and C4, I can take C5. In this graph, you can see that no arrows pointing to courses 0, 1, and 2. This indicates that those courses currently have no prerequisites. So here's my course selection plan. I can take courses 0, 1, 2 first. However, please note that this is just one possible order, which means when it comes to courses 0, 1, 2, the order in which I take them doesn't matter. My sequence could be 0, 1, 2, 0, 2, 1, or 2, 1, 0. In fact, any combination of these three numbers would work, right? Okay, let's just take courses 0, 1, 2 in such order. In this graph, you can see that no arrows pointing to courses 3, 4 currently. So this indicates that those courses have no prerequisite now. So I can continue to take courses 3 and 4 at this time because there is no arrow pointing to course 5. This means there is no prerequisite for it now. So I can continue to finish the course 5. All right. This represents one possible sequence in which I can take courses while following these prerequisite rules. In fact, we have just simulated the process of topological sorting based on our previous example. How did we do that? Let's dive into the concepts of topological sorting. First, let's recall a key concept for a directed graph, the degree. It's the number of head ends adjacent to a vertex. Now, can you figure out the degree for each vertex in this graph? For example, vertex 0, there is no head ends adjacent to it, so its integrate is 0. Vertex 2, there are 3 head ends adjacent to it, so its integrate is 3. Vertex 3, there is no head ends adjacent to it, so its integrate is 0. Vertex 4, there is 1 head ends adjacent to it, so its integrate is 1. Vertex 5, there is 1 head ends adjacent to it, so its integrate is 1. Let's return to our course selection plan example. Vertices 0, 1, and 2 each have an integrate of 0, while vertices 3, 4, 5 each have an integrate of 2. In topological sorting, we follow this process. We remove a vertex with an integrate of 0 from the graph and add it to the topological order. Repeat this step until no vertices remain. Let's start by selecting a vertex with an integrate of 0. We have 3 options, courses 0, 1, and 2. Now for this example, I pick vertex 2 from the graph and add it to our topological sequence. To update our graph, vertex 3's integrate decreases from 2 to 1. I continue removing vertices with an integrate of 0 from the graph. Let's say I remove vertex 1 and add it to our topological sequence. To update our graph, vertex 3's integrate decreases from 1 to 0, vertex force integrate decreases from 2 to 1. I continue removing vertices with an integrate of 0 from the graph. This time, I remove vertex 0 and add it to our topological sequence. To update our graph, vertex force integrate reduces from 1 to 0. I continue removing vertices with an integrate of 0 from the graph. This time, I pick vertex 4 and add it to the topological sequence. To update our graph, vertex 5's integrate reduces from 2 to 1. I continue removing vertices with an integrate of 0 from the graph. This time, I pick vertex 3 and add it to our topological sequence. To update our graph, vertex 5's integrate reduces from 1 to 0. I continue removing vertices with an integrate of 0 from the graph. This time, only the vertex 5 can be selected. I remove vertex 5 from the graph and add it to our topological sequence. At this point, all the vertices in the graph are removed. By this process, we get a topological sequence, and this sorting process is what we call topological sorting. For today's question, the input courses and their prerequisite rules are given as a 2D array like this. Let's break it down. Each sub-array represents a course to take and is represented pair. For example, the left side is the course to take. The right side is its courses prerequisite. So if we say 4, 0, it means to take course 4, we must first complete course 0. We can draw a graph based on this given input. First, I take the course 0, then I can take course 4. Now we say 4, 1, it means to take course 4, we must first complete course 1. Now we see 3, 1, it means to take course 3, we must finish course 1. Now we see 3, 2, it means to take course 3, we must first complete course 2. Now we see 5, 4, it means to take course 5, we must first finish course 4. Now we see 5, 3, it means to take course 5, we must first finish course 3. Now, how can we convert this virtual graph into a format that computers can process? We will use a JSON list to represent this directed graph. On the left side, we store the vertex data. On the right side, we'll use a list to store the outgoing neighboring vertices from that point. For example, vertex 0, its neighboring is vertex 4, so I store 4 in this list. Vertex 1, its neighboring is vertex 4 and vertex 3, so I store 4 and 3 in this list. Obviously, it doesn't matter who is stored first in this list, which means it is also correct if the list is like 3, 4. From vertex 2, its neighboring is vertex 3, so we store 3 in the list. Similarly, you can imagine that all the vertices and their neighboring vertices data in this graph can be saved in an adjacency list. Now let's dive into the coding part. I'll create an array called integrate with a length equal to the total number of courses. We will use an adjacency list to represent the graph. There are many different ways to implement an adjacency list, and today I'm going to use a hash table. In this hash table, the left side key stores each vertex course number, while the right side value stores a list of its neighboring vertices. For each subarray, the question specifies that the left side is the course to take, and the right side is its prerequisite course. This means course 4 has a prerequisite, so its integrate is increased by 1. We check whether the information for this vertex course 0 is already stored in our hash table. If not, we initialize a list, store its neighboring vertices, into the list. In our hash table, the left side stores the vertex data, which is 0 now. Continue the for loop. Now we are looking for the subarray for 1. To take course 4, there is a prerequisite course 1. So here, the integrate of course 4 increases to 2. We check whether the information of this vertex course 1 is already stored in our hash map. If not, similarly, we put this vertex course 1 and its neighboring vertices data into the list. Continue the loop. Now we are looking for the subarray 3, 1. To take course 3, there is a prerequisite course 1. So here, the integrate of course 3 increased to 1. Because vertex course 1's info exists in our hash table, which means we have another neighboring vertex from vertex course 1. We directly add such neighboring vertex into our existing list. You can imagine that after we have processed each subarray for this given input to the array and exit the for loop, we have successfully converted this graph data into a hash map along with the integrate array. This means that the top half of the code block is representing the graph using an adjacency list. Here, we implement an adjacency list using a hash table. So what do we do? In the second half, we want to get a topological sequence based on the graph. Let's record our course selection plan example. In topological sorting, we follow this process. We remove a vertex with an integrate of 0 from the graph every time and add it to our topological sequence. Repeat this step until no vertices remain. At this point, all the vertices in the graph are removed. By this process, we can get a possible topological sequence. And this sorting process is what we call topological sorting. So I use a queue for vertices with 0 integrate, helping me generate a topological sequence. Put all the vertices whose integrate is 0 into the queue. Currently, I can put vertices 0, 1, 2. We use a counter to track the number of courses we can complete, which equals the number of vertices with 0 integrate processed by this queue. If, at the end, the counter equals the number of vertices, it means all given courses can be completed. It will return true. As you can see, this is a typical breadth first search template. We will use BFS traverse this graph. Each time, we will dequeue one element from the queue. Count++ means this queue has processed a vertex with an integrate of 0. I then check the hash table to see which courses are influenced by the completion of course 0. Use a for loop to iterate through this array list. Decrease course 4's integrate from 2 to 1 as it's influenced by the completion of course 0. After decreasing the integrate, we check if vertex 4's integrate is now 0. It's not. Vertex 4's integrate is still 1, which indicates there is one remaining prerequisite for course 4. Continue to dequeue an element from the queue. This time, vertex course 1 is dequeued. Count++. We then check the hash table to see which courses are influenced by the completion of course 1. Use a for loop to iterate through this array list. Decrease course 4's integrate from 1 to 0 as is influenced by the completion of course 1. After decreasing the integrate, we check if vertex 4's integrate is now 0. It's yes. Add vertex 4 into our queue. Continue use this for loop to iterate through this array list. Decrease core 3's integrate from 2 to 1 as it's influenced by the completion of course 1 as well. After decreasing the integrate, we check if vertex 3's integrate is now 0. It's not. Vertex 3's integrate is still 1, which indicates there is one remaining prerequisite for core 3. This time, we dequeue course 2, count ++. I then check the hash table to see which courses are influenced by the completion of course 2. Use a for loop to iterate through this array list. Decrease course 3's integrate from 1 to 0 as it's influenced by the completion of course 2. After decreasing the integrate, we check if vertex 3's integrate is now 0. It's yes. We add vertex 3 into our queue. At this time, vertex course 4 is dequeued. Count ++. I then check the hash table to see which courses are influenced by the completion of course 4. Use a for loop to iterate through this array list. Decrease course 5's integrate from 2 to 1 as it's influenced by the completion of course 4. This time, vertex core 3 is dequeued, count ++. I then check the hash table to see which courses are influenced by the completion of core 3. Use a for loop to iterate through this array list. Decrease course 5's integrate from 1 to 0 as it's influenced by the completion of core 3. As you can imagine, vertex 5 will eventually be dequeued out. Count ++. Since vertex course 5 is not stored as a key in our hash table, program will stop from here and jump out from while loop. If at the end the counter which represents the course of vertices with 0 integrate processed by this queue equals to the total number of vertices, it means all given courses can be completed. This function will return true. Alright, I hope you enjoyed this video. If so, please like and subscribe. Thanks for watching. I'll see you next time.